Hey everyone, welcome to this explainer. Today, we're going to untangle a really fascinating visual puzzle that just so happens to double as a classic coding problem. It's called bipartite graph validation. So if you're into structured logic and, really clear visualizations, let's figure this whole thing out together.
Okay, so imagine you're given a really simple rule for a game. You've got this network of connected dots, and you're handed exactly 2 colors of paint. Your goal, paint every single dot. But of course, there's a catch. No 2 dots connected by a line can share the exact same color. Sounds like a totally simple, relatable game, right? But mathematically speaking, this right here is the absolute core challenge of validating a bipartite graph.
Now, in a coding environment, a simple graph is typically presented as an adjacency list. Basically, a given index tells us exactly which nodes it connects to. And our fundamental rule for today is to figure out if this graph is bipartite. To put it simply, a graph is bipartite if its nodes can be colored in one of 2 colors in such a way that absolutely no 2 adjacent nodes are the exact same color. So here's our roadmap for this explainer. First, what is a bipartite graph? Second, the graph coloring strategy. Third, spotting a graph failure. Fourth, handling disconnected components. And finally, implementation and complexity. All right, let's jump right into section 1. What is a bipartite graph? Dividing nodes into sets.
Before we even think about writing a single line of code, we really need to understand the structure. Basically, if the nodes of a graph can be completely divided into 2 distinct sets, let's say set 1 on the left and set 2 on the right, with the connecting edges only running between nodes from different sets, well, then the graph is bipartite. Notice how we can literally visually rearrange this pentagon-shaped network to perfectly bridge across the 2 groups. It's perfectly clean. There are 0 edges connecting blue to blue or orange to orange. But wait, what happens when a graph isn't bipartite? Well, when we try to force this new graph into our 2 sets, we instantly hit a brick wall. Notice that red dashed line? It's pointing to a connection between node 2 and node 3, or node 4 and node 3. Because of how they're wired up in the original shape, there's just no way to avoid an edge existing between 2 nodes in the exact same set. It's completely impossible.
Moving right along to section 2, the graph coloring strategy, or as I like to call it, the paintbrush rules.
So we're going to transition from that abstract idea of sets into a super practical, highly visual strategy. We are literally going to use blue and orange paint. Here's how it goes. First, you pick a starting node and color it blue. Second, find all of its immediate neighbors and paint them orange. And third, we just repeat this alternating pattern as we travel through the graph. For our explainer today, the traversal algorithm we're going to use to actually pull this off is depth first search, commonly known as DFS. All right, take a look at this blank 5-node graph. It is fully ready for our coloring algorithm. Actually, I want to challenge you right now to just mentally apply those 3 steps to this blank canvas before I even show you the answers. Just imagine starting right at the top and working your way through. Okay, let's go ahead and execute our DFS. Step 1 is establishing our starting point. We're going to target node 0, right up there at the very top of our graph. Boom, there we go. We successfully color node 0 blue, and that officially kicks off our entire algorithm. Now moving to step 2. Our depth first search tells us we need to dive into the neighbors of the node we literally just colored. So we've got to transition from node 0 right over to its neighbor, which is node 1. Since node 0 was blue, our golden rule dictates that all of its neighbors absolutely must be colored the opposite color. So we make a DFS call to node 1 and, yep, we color it orange. We are off to a pretty perfect start here.
Okay, section 3, spotting a graph failure. This is where we encounter the dreaded color clash.
Let's just walk through the rest of this DFS process. Node 1 is orange, right? So its neighbor, node 2, has to become blue. Node 2 is blue, which means node 3 becomes orange. But hold on, look at that final frame on the right. We just hit a massive issue. We arrived at node 4. Because its previous neighbor, node 3, was orange, we absolutely have to color node 4 blue. However, one of node 4's other neighbors is node 0, and it's already colored blue.
This adjacent color match is the whole ballgame. We've been carefully coloring alternating nodes right from the start, but encountering a situation where 2 connected nodes are the exact same color, like our blue node 4 directly touching our blue node 0,
That means there is absolutely no way to color this graph differently without breaking our core rule. Therefore, this graph is mathematically not bipartite. Failure confirmed. Which brings us to Section 4, handling disconnected components, basically the hidden trap. Now, you gotta keep in mind, the input isn't always gonna be a beautifully fully connected graph. Sometimes it could be a graph with multiple completely fragmented components. Think about it. If we just run our DFS starting at node 0, our algorithm will flawlessly map nodes 0, 1, 2, and 3. But it will completely miss nodes 4 and 5 because, well, there are 0 edges connecting them. That is a huge trap.
So how do we safely navigate this trap? We have to ensure we check every single component. Our code actually needs a built-in safeguard, basically an iteration through every single node. If we scan and find an uncolored node, like node 4 over there on the right, we have to trigger a brand new DFS starting right from that node. Only if all the components can be colored with our two colors without a single clash, only then is the entire graph validated as bipartite.
All right, final section, Section 5, implementation and complexity. Let's translate these visuals into actual code.
Obviously, in our code implementation, we don't use literal buckets of paint, right? Instead, we map our colors to simple integers. We'll represent blue and orange using the numbers 1 and -1. And to keep track of the whole shebang, we create an array called colors, initially filling it with zeros. A 0 just means unvisited node. So as our DFS explores the graph, we are continuously updating this colors array, swapping out those zeros for ones or -1s.
So how efficient is this strategy in the real world? Let's quickly break down the big O complexity. For time complexity, we're looking at O of n plus e. Why? Well, because our DFS algorithm systematically explores n number of nodes and traverses across e number of edges. We basically visit everything exactly once. For space complexity, we are sitting at O of n. That space is required for two main things: our colors array of length n and the recursive call stack for our DFS, which in the absolute worst case scenario could grow as large as n.
And there you have it. That's exactly how you solve the bipartite graph validation problem. But before we wrap up this explainer, I want to leave you with something to chew on. You see, this isn't just some abstract coding exercise. Being able to split a network into two distinct, non-conflicting sets is literally the foundation for solving some massive, real-world problems. We're talking everything from scheduling university exams without double booking students to perfectly matching job applicants to open positions. So the next time you're looking at some wildly complex web of relationships, ask yourself, could you entangle the whole thing with just a simple two-color strategy? Thanks so much for exploring this with me today.